Yeah, I think Ken said that your assignment this week was based on power test and also tidying data, right? So it's kind of like you're doing two different things. Maybe the power part will come in if you guys have. I'm not entirely sure the power part is like set in stone, but I'm sure you probably will be tidying up data. So what I'm going to do is at least I'm going to go over the top 3 things as it pertains to, I'm going to go over the top 3 things in tidyverse, which I think is mutate, filter, and select, right? So I'm going to use empty cars because each of those things is something different. So have you guys ever heard the mutate function? So I'm just gonna first use, I guess, maybe I'll use empty cars. Right, so I'll just call it this. So have any of you guys heard of the mutate function? I don't know if Ken has shown you guys this yet. So I want to make sure that I'm keeping consistent with what's been done in class. Yeah, it creates a new column. Yeah, so it creates a new column, Eddie. Great. Yeah, or modifies, exactly. So there's 2 things, right? So I'm just going to make a note of what Eddie said because it's true, right? So mutate does a couple of things, but the thing is really it creates new variables. So you can either, create a new variable. And usually when you create a new variable, you're creating a new variable based on the other existing variables you have in your data set, create a new variable, or the second thing is that you can modify existing variables, right? So that is especially true if the way in which your variable is presented, or even the label, it's the way in which your variable is presented is not ideal. Maybe it's not even a numerical form. You want to take a mean. Really, the whole point of tidyverse is that it's supposed to make things more efficient, right? So you can imagine that instead of having to actually create new variables outside of your data frame. So if I were to use it in base R, instead of actually appending my new variables to my data frame, I would have to create these variables externally and then aggregate them using the data.frame function, which is very inefficient based, right? So the thing about tidyverse is more efficient is that if you keep appending things to the left, you can actually update your data frame without having to actually do it externally outside of your actual data set, which is more efficient basically. So when you the .1, it just, the thing is that that's kind of like how it's like how R kind of stores the number of variables. So if you have more than one variable, we'll just say var.1, var.2, etc. Right, so we'll just keep updating your variables, right, according to right. If you don't have a label for your variable, it does that. So that's usually feeds you var.1 and var.2, whatever. If you don't actually have a label and it's giving you one manually, so you can actually change that to whatever you want. No, yeah, not an index, because var1 where you have an index actually means pull out the first observation or something. It has a different meaning. So when you put var1, you're actually saying pull out a particular observation or pull out something, right? That's completely different from just labeling. So var1 means pull out or extract something. So you cannot do that. When you use an index, it just means pull out. So it has a different meaning than when you put var.1. That's why they don't do var1. It's because that has meaning, right? So that's why it wouldn't work. You can actually try it and see as well. What happens if you take a variable and you say 1, it will probably pull out the first observation you have in your thing. So that's why it doesn't. That's not why it doesn't do that, right? It already has a function in base R. Okay, so let's download tidyverse. Yeah, so it already has a role, right? So the thing is, that's why it doesn't index like that. Okay, so I gotta say, in assignment 1, we noticed a lot of things like this, where this was loading. Please hide it. It's very difficult to read things, and then it doesn't look sightly because you can see that it takes up half of the first page. I'm pretty sure people in my tutorial who were not in my tutorial probably did this, right? Because I think I told my students not to do this, but the thing to do when you have this kind of thing, because when you run, if you don't actually say like message equals false and warning equals false, it will actually load this into your assignment. Right, and that doesn't look great, right? So, and you can imagine that sometimes your presentation is, you know, sometimes stylistically it matters, like how your thing, how you compile your ideas, even the way you present it matters. So please be a little bit clean, right? Try to hide that stuff. Yeah. Anyways, let's go run with Eddie's theory that we kind of think that MT-cars allows us to mutate allows us to kind of add new features to our data frame, right? So if I look at just what I have, if I just, you know, preview the data, what do I get? I get something that looks like this, right? So I think there's actually 11 columns, so it keeps going on like this. But I might want to do something like, I might want to shift up the mean or something, or maybe I want to create I don't think you guys have learned linear regression yet, but it's entirely possible that if you want to build a model or something based on linear regression, you may want to rescale variables, right? So if you want to rescale by the mean, you can do the following, right? So maybe you have something like the following. So data 2, right, is going to be equal. So the first thing you have to do is you need to feed it your original data frame. Then, you know, you're always going from left to right, right? It's a left-right sequence. So if I want to add something, right, let's suppose that, like I said, I want to recenter my variables, right? So because in linear regression, we tend to recenter the predictive variables are on the mean. So in linear regression, you have something that says y is equal to, you know, mx. Maybe I'll just do it in paint. Just something that looks like the following. Linear regression, you don't need to know this, but I'm just going to give you context to why I'm going to change this variable. Something that looks like the following. You know, y is equal to mx plus b, which you guys probably saw in high school. So, you know, you have the rise and the run. Whenever this may be the response variable, right? And this could be actually the predictor variable. Sorry, x is the predictor variable. And then you have the relationship that the slope is a relationship, right? It's entirely possible that you want to recenter your variable x right around the mean for various reasons. One, to reduce correlation, which is kind of a funny thing. It's almost macroscopic, but anyways, to reduce correlation, or even if you have more than one predictor variable, but just to improve interpretability, right? So let's suppose we want to actually recenter our variable. We can just do something like the following. So I guess weight is already itself kind of continuous. So something like weight minus, so weight is going to be equal to weight minus the mean of weight. And let's see, this is me recentering it. When you recenter things, you always recenter it around its mean, kind of like something you see, like a standardization basically, something we kind of see a lot in normal set, like things that are normal, like things are symmetric. So if we do this, what do we get? Oh, it always gives me heartache sometimes when I run this. There you go. You can see that it ran, right? But now let's think, because our initial data frame, if you look at the dimensions of our initial data frame, it was what? It was 32 by 11. So now if we look at the dimensions of data 2, it should add another one, right? So now let's look at it. Let's see what we have, right? So I can show you guys what it looks like. It's going to be somewhere. Oh, this is the original one. So if I look at data 2, I guess we'll just put it in here so you can kind of see. You will see that, let me just use this. You will see that it creates this wave thing here, right? You can see that it's actually negative. That's probably because when it's negative, it means that the weight is actually less than the mean, right? So that's when it'll be positive when it's bigger than the mean, right? So it oscillates depending on whether or not it's bigger or less than the mean. And so you get this new variable, right? So notice that it doesn't actually remove the previous variables, right? All it does is, so here we've created a new variable based on the variables we have that are existing. But as Eddie said, it's also entirely possible to modify variables, right? If you don't like, modify variables you have. If, for instance, your variables are numeric, but they're presented as a string, you can create a new variable that says as a numeric of your old variable, and it's the same new variable. So you could rename a variable that maybe it's in string form, which you want to be numerical. But you can see that it does, it adds an extra feature and adds an extra column to your data. Why is this efficient? It's efficient because think about what you'd have to do beforehand. In base R, you'd have to actually take the mean of weight, then create the variable externally. So you need to do weight minus the mean of weight as a variable externally, then add it to a data frame, right? So you need to do the following in base R. Base R, weight equals, you'd have to do, weight dot the mean of weight. And then you need to do the following, you know, data 2. Let's call it data 3. So you can see here that you've actually made 2 steps, right? You do data and then weight, right? So you can see that here I've actually done 2 steps. This is 2 steps, right? So this is very inefficient in some sense, right? Which is why we tend to use tidyverse. And tidyverse, all I have to do is just run one pipeline and the whole thing goes for me, right? So now you might also think that there might be, in your assignment, you'll see that Ken will ask you to do things like filter. So select based on certain rows or certain columns, right? And then you should obviously know how to perform such a thing. So I'm gonna just reorganize things so you guys can kind of see. So what if he asked you, for instance, in your assignment, you know, you have a series of mice and only select the mice with a certain weight range, basically, right? So you might be interested in you know, partitioning based on a particular feature. So does any of you know what filter does? Like what does filter do? It does something. What do you guys think the filter does? So filter and selector are kind of both things that cut your data frame down, but in opposite ways, right? So filter actually removes rows on your data frame, right? And so, you know, and this should be actually select. Select actually removes columns. So filter actually, you know, the primary role, you're subsetting your data based on a particular, subsetting your data across the rows. Right, so you don't want every observation, you only want observations that satisfy a particular criterion, right? So in our, for example, our weights, in our thing, we know that if we look at the features, if we look at help, let's say empty cars, we can actually subset based on any criterion we want, right? Especially if the variables, especially if the thing we're subsetting on is like the categorical, and you can use a logical operator, like either the statement is true or false, and you can subset in that way, right? So if you're any discrete math, if you have a statement about, if you have a Boolean, if you have a Boolean, you can create a Boolean variable in some sense, and R is creating a Boolean variable inside the tidyverse. Like when you give a statement and you filter based on a condition, it will create a Boolean series, and then it will evaluate the truth of the statement. And if the statement is false, it will drop that particular row off your data set base. That's what it's doing, right? So here we can see something like CYL is number of cylinders. So maybe we want to, so if we look at the table of CYL, we can see that, so number of cylinders it can be correlated to your weight, basically, right? So if it's correlated to your, and we can actually show and see, so you can see that number of cylinders is correlated to your weight. There's 3 different classes, 4, 6, and 8. Now let's suppose we want to look at the scatter plot of weight against, I don't know, weight against what else is continuous? Weight against your, I guess there's something else there that I wanted to use. What is it? Yeah, weight against your miles per gallon. Let's look at it. Let's look at a scatter plot here to see why we might actually want to subset. If we look at weight against gallon, so I'm going to give it, I'm going to put in data 2 AS X equals. So naturally, obviously, you would imagine the weight of the car might be associated, might influence them how many miles per gallon you go. So I'm gonna call weight to be the on the x-axis and MPG on the y. So I'm gonna do a scatter plot here and see what I get. You can actually see here, right, that and if I do something even more crazy here, let's see if I color equals, okay, color or fill equals CYL. Let's see if it works. Oh, it doesn't. Why is it doing this? CYL, maybe I just don't, yeah. Oh, it's not what I wanted. Oh, I know what the problem is. Okay. It started, whatever. I kind of wanted to show like that the color is going to change. I wanted to show the color out. I wanted to show that you have 3 different levels For some reason, it's not cooperating with me this morning, so I don't know why. Maybe it's color. Let me see. Yeah, there you go. I had the wrong thing. Yeah, so you can see here that if I put weight against MPG, so I might think that the weight of the car might influence how many miles it goes per gallon, or how many miles per gallon it uses. But you can see here that when you factor according to color, there's 3 different scales, right? In the sense that it moves the fastest with the lightest car, which intuitively makes sense, right? It will move slower when your car is heavy. And you can actually see here that it's moving the slowest in some sense with the heaviest group, which is group 8. So if you want to do a linear regression, for instance, model that's based on weight against MPG, you might actually think to yourself that there's something different about these 3 different groups. So you may want to split your data, and you may not want to do a linear regression model that aggregates them all together. You may want to make different models based on different weight classes, because you might think weight is too significant to just put it into the model as a fixed thing, right? So you can see that because you have these 3 different levels, you might think that it might make sense to do linear regression on different groups instead of putting them together in one set of observations. This is why you might. So, we can say notice that there are 3 different weight classes that influences the relationship, right, between weight and MPG. We may want subset based on cylinder class, right? So the cylinder class, if you have, obviously the cylinder class is, if there's 8, it's kind of probably a bigger car. So maybe we want to create a data set then that only includes cylinder class 4 and 6, right? So then the question is, how can we do this then? Well, let's create data for, or let's call data 4, I guess, which is going to be equal, which is going to be based on data 2. But now I'm going to filter. So whenever you want to filter across, we want to remove a set of observations based on a criterion. Usually that's filtering. So you might say, what is the difference between filter and select? When you want to subset your data, your observations based on a particular characteristic, this is filter. Select is when you want to choose a certain set of variables from your data frame. This is not the same as choosing observations, right? So choosing observations versus choosing variables, this determines whether or not you're using filtering or select in tidyverse. So remember this for your assignments. If he asks you to subset based on observations, you are using filtering. But if he asks you to subset based on a set of variables, right, you're using select. It's most likely the case in your assignment you'll be using filter, because it doesn't really, there's nothing for him to ask for you guys if to use select, because this is not a course in data science. So it doesn't make sense for him to ask you necessarily to clean your data up, and only if you're trying to tidy your data and make a nice data frame would you think about the select. But that's not the point of this course, right? The point of this course is to introduce you to data analysis, and so you'd probably be using filter. But just keep in mind, if he does ask you a question on select, sorry, on subsetting variables, then you'd be using select. But let's see. Let's suppose I want to just filter based on a condition, right? So I only want to choose the CYL such that it's equal to 4, right? And actually I want to see, yeah, or, right? So you can see that this is a logical, this is a logical operators I'm using here, right? Which means that technically speaking, the filter function is going to create a Boolean series about the truth, right? So that if your CYL is actually not equal to 4 or 6, it will just say false and cut it out of your data frame, basically. So this is what it's actually doing, right? So if I do CYL equals to, so I'm actually asking for these 2, right? It's not, so let's see if this runs. It does. So be mindful of the fact that it's not, you cannot just do this. You have to, unfortunately, sometimes R can be a bit rigid, although far less rigid than Python, in the sense that you have to repeat CYL twice. You cannot just say equal to this or this. This will not run, right? So you cannot do this. It will not run. You have to put the syntax twice, basically. It's a little bit rigid sometimes, but anyways, not really. It's very logical that you're asking to do 2 different things. So you should probably put 2 different statements. So let's see what happens when we look at our data frame. So first of all, the dimension of the thing should certainly be less by a factor of how many observations had CYL of 8, basically. Well, let's see. You can see it's 18 by 12. The initial one was actually, I think it was 32, which means that there are probably 14 cars that have cylinder class 8, I want to say. So if we look at our data, then you will see the only thing that's left are those of cylinder, right, 4 or 6. So you can see that this is 6. And if I go tail of the data, so tail of data 4, I also get, you can see that it's 4, right? So you will not see 8 previewed anywhere. You can check if you're not sure by looking at the summary of CYL, and we'll show you that it's the maximum is 6. There's no 8, right? So we can actually check ourselves. See, oh, sorry, I should really see data for CYL. You can see that the maximum is 6 instead of 8, right? Okay, cool. So the last thing is that the select function, which I did say is probably, you know, it may be a little less, what do you call it, common in this course than filter, but anyways, you may see it. So here in select, you are selecting across the rows. You are selecting across rows rather than observations. So this means that you have the ability to remove variables we're not interested in, right? So, however, you have not removed any observations using this. So if your goal is to remove a set of observations, this is not the function to use, right? So keep this in mind. This is not the function to use if you want to remove a certain set of observations, right? This is not the function to use. If that would be filter, right? Okay, now I want to show you guys something cool. I'm going to show you how, I'm going to show you guys a linear regression, which I know I just want to show you guys how it works. Definitely, you don't have to know this, and don't panic. Feel like, oh my gosh, like, you know, I don't, you know, he's going to ask us linear regression. He's probably not, you haven't learned it yet, but I do want to show you guys why you might want to select certain variables. So I'm going to, you know, pretend I'm going to do linear regression, at least in ggplot. So I'm going to select the variables I need to do linear regression. So for linear regression, you guys know that it's looking at linear relationships, which means that your variables have to be continuous. At least the response variable has to be continuous, right? It does not make sense to talk about linear regression when your response variable has very discrete outcomes and it's not continuous. That wouldn't make any sense. So it's something we use when we're looking at it, you know, like a response variable that's linear or like kind of, you know, continuous. Okay, I'm going to then pretend that my MPG is my response variable, like how fast you're going, as a function of, let's use our new weight variable we created. Instead of using WT, let's use the weight variable we created, and let's see what we get. So I really only need 2 columns because, you know, I only need the one, to do a linear regression, I only need the X and Y. So let's call it data 5, where I'm going to subset based on only the things I want. So let's go back to the initial data frame. Right, so let's now look at the previous one. So we're not removing observations here, we're removing columns. I'm gonna then go back and use data 2, not data 4, which we removed some stuff. Okay, so I'm gonna use select. What I really want is only MPG and weight, right? So the dimension of this data frame is going to be 32, at least across the observation space, but it should only be 2 on the column space, right? So if I look at this, what I get is 32 by 2. Cool. Now let's do a cute little linear regression plot, which I'm totally cheating, but anyways, he probably will show you scatter plots this week or some point, right? So he probably did. Everyone knows what a scatter plot is, so it's not like I'm not reinventing the wheel here. Okay, so let's put in data 5. And now I'm going to say that X is weight and Y is equal to mpg plus. Now, if I want to do some kind of smoothing effect, so when I say I want to do linear regression, I'm gonna incorporate a smoothing. When you want to do linear regression of some sort, you put geom smooth, because you can see that, you see how it says method equals. I'm going to put method equals LM as in linear model, basically, right? So LM means I'm doing a linear model, and that's what it's going to do, a line of best fit for me, basically, right? So when I look at this, what I get is the following. So you notice that I get this line of best fit, which is the blue line, and the observed points you see are the points across the line. So obviously the how good the model did, and you can see here it says formula Y is a function of X. So how good the model did? Well, actually that is, that depends on how closely the actual points follow the blue line. So the blue line is actually where all the theoretical points happen to sit. In some cases, the actual model exactly approximate the points followed. So when it sits exactly on the line, the model did pretty good. But when it's far from the line, it didn't do as well as it should. But does anyone know what this gray thing is? You guys talked about this in class a bit, but maybe not in this context. You guys know what this gray line happens to be? What's the gray line? Do you guys know? That's okay, Eddie. Any answer is fine. That's actually the standard error, basically, right? So this is actually the standard error. That's the standard error you're seeing. So whenever you have any of you guys heard of confidence intervals? It turns out that these gray lines you see are actually standard errors, right? For your line of best fit. And you can see that the standard error is actually smallest over here because the model did the best. But when your model performs poorly, you can see the standard error actually increases at the ends where it did pretty badly. Yeah, so if the points are really far from the blue line and the model it's regions where the model underperformed, right? Really, ideally, you'd like your points to be close, following the blue line pretty closely, right? So no model is perfect, obviously, but obviously you want your model to do pretty good. But you can see that the standard error is actually increased, guys, when you move far from the center, because the model is the best here. You can see that the points are kind of close to the blue line, but the points are kind of scattered over here because the model didn't do as well, basically. So that's why the standard errors are bigger here. And I think that Ken defined the standard errors for you guys as the standard deviation divided by root n. So that's what they're actually showing here. They're actually showing that standard error, which means that if I want to remove that, I would just do the following. So I can remove that if I want to. It'll be standard error equals false, right? So if you do this and you rerun the whole thing, you will actually remove that feature, right? So that's kind of neat. Yeah, so it's kind of cool, right? Yeah. Yeah, so you can see now it just looks kind of like this, where essentially you have no standard error. So generally speaking, I don't think that people would have this kind of line when they submit it for publication, because we do want to see the confidence bands most of the time, right? So generally you wouldn't put standard error equals false, because that wouldn't make any sense in the context of like trying to actually get an assessment of how your model performed, right? So the standard errors tell you if your model did very poorly or not, so you tend to keep them. But anyways, the point is not even linear regression. The point is that you can see that I'm able to create a linear regression model because I removed the variable that I wasn't interested in, and then now I use the data frame that I created here, which is just literally 2 variables to create this new data frame that allows me to make this model. Now I'm going to move on from this topic because I want to talk about power, because this is not so easy to understand, and I want to make sure I spend about 20 minutes on it, because this part is sufficiently tricky. And I know you guys will have questions, which is good because then people who haven't attended will also be able to ask me questions, or will be able to watch the video and then inadvertently ask me questions because you guys are asking me questions. So what I want to talk about is the following things. Power is actually related to two things. Has Ken discussed power with you guys? I think he might be discussing it this class actually for this week. So probably the answer is no, but you will see it this week. Okay. So the power is actually what? The power is not actually alpha. It is something else. So have you got, everyone knows, or at least hopefully they know that, I cannot find my, I have to not use it until I find it. Okay, so anyways, everyone knows that alpha is equal to the probability of a type 1 error. Right, which is the projection, which is equal to, to be very pedantic here, this is equal to the probability of rejecting the null hypothesis, given that HO is actually true. So that's what that is, right? Of course, that is problematic, right? So you can imagine that in the court of law, when you reject the null hypothesis when it's actually true, that means that you've actually convicted someone who's innocent. So that's pretty problematic. So we want to make sure that we haven't made that mistake. Right. So this is why we actually screen. This is why we want this to be low, right? So we want this to be low so that we don't make mistakes where we have falsely rejected the fact that there's no effect in our study, right? But power is actually the opposite. So if beta is equal to the probability of a type 2 error, does anyone know what type 2 error is in relation to type 1 error? What is type 2 error? This is kind of almost the opposite of type 1 error. Does anyone know what that is? Have any of you heard of it? I guess most of you would have taken B57, so you might not have heard of it. The type 2 error is actually rejecting the alternative when it's actually true. So you can see that it's rejecting HA when it's actually true, right? So that's also problematic because if you think about the court of law, that would mean that you actually let someone that was guilty walk off free, and that's equally as problematic as convicting someone that's innocent, right? So we don't want to make either mistake too often, right? And so it turns out the power is actually 1 minus beta. That's actually power, right? So it's actually related to type 2 error in this way. It is the complement of beta, right? So we obviously in any research study, you want to maximize the odds of finding an effect in your study, right? So most of the time you want to find that scientific evidence that says that there's some kind of significant result, and so you want your power to be high. And this is why the power is high, of course, when beta is low. Right, so if you're probably making type 2 error is low, then of course 1 minus beta is going to be high. But if the beta is getting too big, then of course your power is getting small, basically, which is not good, right? So it turns out that the power is related to a couple of things: the sample size, the effect size, and the effect size is actually the difference between. So if this is your actual, if this is the null hypothesis, and maybe you say mu is equal to mu naught. If the effect size is actually the extent to which your effect is bigger than 0, or far from 0. Right, so the effect size is the extent to which your thing is far from 0. So that's a good question, Eddie. So I'm just going to finish the effects. So Eddie is asking if beta increases, alpha decreases. I will say that if you know that, if anyone knows about an optimization problem, basically a convex optimization problem is one where a maximum exists, right? So in a convex optimization problem, a solution exists, right? That is unique, and there's a maximum, right? At least if there should be at least a local maximum, perhaps even a global one. But the problem with beta and alpha is that they're not in the same space. So a convex space means all the set of solutions need to be in the exact same space. with beta and alpha, they're in actually because alpha is actually referring to a type 1 error, which is in the null space, and then beta is referring to a type 2 error, which is in the alternative space. The actual space, they're not in the same space. As a consequence, you cannot find a one unique solution. Like there's no global maximum. There's no optimal solution. So that means that they cannot both increase at the same time. And similarly, they cannot both decrease at the same time. So I'm going to repeat it again. Unfortunately, because because alpha is in the null space and beta is in the alternative, they don't actually sit in the same solution space. As a consequence, you cannot decrease them both at the same time, which means that if one is decreasing, by definition, the other one has to increase, but you can try to make them both small, right? So unfortunately, if beta increases, it means that if you decrease alpha, then beta increases. So what's the context here? If you decrease alpha, it means you are less likely to reject the null hypothesis when it's true. That's what it means when your alpha decreases. It means you're less likely to make a type 1 error, so you're less likely to reject the null hypothesis when it's true. But if you are less likely to reject the null, you are also less likely to accept the alternative when it's true, because you cannot do both at the same time. You cannot simultaneously accept the null and the alternative. So if you're more likely to accept the null, you are less likely to accept the alternative, and you're more likely to make a type 2 error. That's why one has to increase and the other one decreases. Does that make sense, Eddie? So unfortunately, because you're more likely to accept the null in some sense, you are less likely to actually, see when the alternative is true. So that means that beta has to unfortunately increase. So they cannot, that's a great question you asked. Unfortunately, they cannot both work in the same direction. That's one thing, that's one great question you asked, because I noted it here. Basically, we have to contextualize this when we're thinking about power, because we always want to make alpha small, because we don't want to make a mistake of rejecting the null hypothesis when it's true. But unfortunately, when we try hard to not make this mistake, we have to also make sure we're not making the other mistake where we are, rejecting the alternative when it's true. So it's a very delicate balance, but there's no optimal solution because they don't live in the same solution space, unfortunately. So great question you asked. And that gives me a great starting point, because, right, you can see, I keep using the empty card example, but it's a built-in data set. Anyways, I'm going to do a t-test. I know that the true mean is like 3.21. So this is the t-test I did last week, where I kind of contrived it a bit. I know this is going to lead to a significant result, because you can see that the weight here, the actual true weight, which is 3.2, the true mean is 3.21, right? So if you look at the mean of weight, it's actually 3.21, and it's pretty far from 2. So this is where I said that the effect size does actually influence the significance. When your effect size is large, that means that your actual sample data is far from your null assumption. You will see a very small p-value, right? And this you will see a small p-value, but also because the effect size is so large, it will also reduce it will also increase your power, because it will reduce type 2 error, right? So if the null is that, if the alternative is truly actually true and you have a very large effect size, you are more likely to reject HO when you have a very, very big effect size. When your effect size is getting smaller, you see that your p-value will actually increase, which will shrink your power. So let's see how this works. Let's run the test here. You can see that if I look at this thing here, I get that the p-value is really small because my effect size is very big, right? So notice that the difference between, so my actual X bar is like 3.21 to the dot. My null assumption was that it was equal to 2, and that's pretty far from each other. 3.21 is pretty far from 2, and the data set where there's only 32 observations. So it's saying that there's a significant result. Now here's the thing, guys. If I actually reduce the effect, so if I actually reduce the effect size, I could actually, if I reduce the effect size, for instance, to, let's say, I make my mu something like 3, right? You will see that because the effect size is so close, because 3 is so close to 3.21, you see the p-value is now bigger. Because the p-value is bigger, unfortunately, your power is lower. You are actually less likely to reject HO. So you're obviously less likely to accept the alternative. So that's a thing we contend with, right? So you can see that the effect size certainly matters. If you have a very big difference between your null hypothesis and what your data shows, you're more likely to reject the null hypothesis, right? But there's also other things to consider. One thing to consider is actually sample size, right? So it's actually the case that, so Ken was talking about the standard error before, and the standard error, to be clear, guys, is actually S divided by root n. So it's a function of the sample size, right? So you guys know that your t statistic is actually the following. It's actually y bar minus mu divided by S over root n. And it turns out that if this denominator, guys, is actually really, really, if the denominator is actually really, really small, it makes the t-value very big, right? So we know that we're going to reject the null hypothesis if our evidence is in the tails here, right? And so that means a very large t-test yields a very small p-value, right? And so your t statistic is likely to be big when your standard error is very small, right? So, but your standard error is small, right, when your sample size is big. So it's patently clear to see here that when you increase your sample size, this whole thing shrinks, which blows up this t-test. So this is why we have sample size considerations. When your sample size is very small, it actually makes your standard error big. What does that mean? It means that the variability in your data is so big, right, that you cannot find your actual test effect. Or if your variability in your data is too big, you cannot find the test effect, and this whole t statistic will shrink, right? So we can actually run that ourselves and see, right? So I'm gonna contrive this a bit where I kind of know, and I want to see where I kind of know, for instance, that this is normal. So I'm gonna sample something I know that's normal, right? So you can see that I set the seed so that I can keep getting the same numbers again. If I do not set the seed, so if I just pull something that's normal, so I'm gonna set the seed because if I don't, let's see what happens. So our norm, let's say, so here I'm doing a mean of a sample of 10, 10, 3, 1. You can see here that if I don't set the seed, it will keep changing my, what do you call it? My values a little, oh, that's close to the seed, that's why. So you can see that it will keep, if I keep generating if I generate the new values of thing, it will keep changing, right? So the reason why I set the seed is because it will keep changing if I don't. So I want to get the same numbers continuously. So that's why I set the seed. Again, if I don't, it will keep changing. You can actually set whatever seed you want, but it will just pull from a different part of the list and you'll get different numbers, and you can set the seed to whatever you want, right? Anyways, you can see that this mean, this is not a trivial mean. I know the actual mean is 3 because I sampled that way. But I'm gonna do a t-test where I hypothesize the mean is 2. Because I know the actual true mean is 3 because I sampled from that data, it should give me a p-value that is actually going to say reject the null hypothesis, right? So you can see that the p-value here is pretty low, even though my sample size is only 10, right? The sample size is only 10 and yet the p-value is small. But let's see what happens if I increase my sample size to 100, for example. You will see the p-value goes even smaller. You notice it was like 0.001 before, now it's the -16. Again, this is because of this phenomenon here, where you can see that it's shrinking your actual standard error. So the t-test is actually blowing up. The t statistic is actually much larger here. It's like 12.36, whatever. Up above before here was 4.58. The reason why it's now 12 instead of 4 is 3 times bigger now because your standard error is a lot smaller. So it blew up your t statistic. So sample size actually truly matters in this framework, right? Those things influence power. Now the other thing that influences power is my p-value, right? If you change your p-value to be, I remember Eddie asked, is it true that if your alpha decreases, it means your beta increases? Yes, it does. If beta increases, we know that the complement of beta is power, so your power will decrease. This means that if I create a function where I'm doing a t-test and I change my p-value to something like 0.01, which is lower than 0.05, this will actually make my t-test, it will make my significance, my power, it will make my power smaller, basically, right? My power will actually shrink because my p-value actually got small. So I'm actually less likely to reject the null hypothesis because I actually decreased my p-value, right? So I'm making it more hard to reject the null hypothesis. This is a function here where you can see that it's going to simulate 1,000 times an R norm from the mean of 10, mean of 3, and it's a sample size of 10. So you can actually change this for yourself and see what happens if you change the sample size to 100, for example. You can see it's doing a t-test. It's going to map my data. It says map to a t-test. It's going to map to a t-test where it's going to take this value, it's going to put the value of x here. So it's going to take these x's here and put it in here. And it's going to keep running the test 1,000 times. So you're actually going to get 1,000 different p-values, as you can see here. And it's going to compare the p-value to 0.05. I guarantee you guys, if you set your p-value to 0.01, instead of 0.05, your power will go down. Right? So you can play around this function yourself and see what happens. It will actually shrink your power. So here you actually have the following. So let's see what we have here. We have, what did I get? I know I did something. Oh, yes. So let's look at, we have 191 divided by, so let's look, the p is going to be the following. 1,000, I guess, right? So you can see here the power is actually, so this is beta. So what I've computed here is actually beta. So this ratio, by the way, guys, is actually power. Sorry, it's beta, right? So this ratio is actually beta here. And so 1 minus beta is the power. Usually the power we aim for is 0.8. But if I reduce my p-value to 0.1, you guys will see that it will probably shrink my beta, right? So you can see we'll actually shrink my beta in a way that's kind of, so you can see here that now my power is actually going to be equal to, oh, let's see, where is it? So now I actually have the following, I have 448 divided by 488, oops. So you can see that my actual, so oops, 488 divided by 1,000, it's like 49%. So now my actual power went down to 0.51 because I dropped my beta in such a way, right? So when you drop your beta, you actually drop your power. So when you drop your alpha, you drop your power. For the reason Eddie asked, if your alpha is decreasing your beta, if you decrease your alpha, you will increase your type 2 error, and that will decrease your power. You can mitigate this a bit by increasing your sample size to like 100, for example, right? So if you change it to like 100, you'll see that it will improve a bit, right? To like, you see it improves to 100, improves completely. It says 100% true, so you literally have a p-value of 0. So if you increase your sample size, you can mitigate a very poor, if you can mitigate having a low alpha, but these are the ways it works. So they're working interchangeably. So if you drop your actual alpha, you have to increase your sample size and vice versa. If you drop your effect size, you have to increase your sample size, etc. But I'll stop here, pause and wait for the next group of students. And I will post, I'll take a pause and I'll post this for those who are leaving. You'll see the second half of the lecture when I post it to my GitHub and YouTube after. So have a good morning, everyone. Yes, that's true, Eddie. That's exactly correct. So if your t-value is big, you will have a smaller p-value because it's further into the tails. I guess I deleted it, but you can see it's further into tails here, and that makes you a lot more likely to reject the null hypothesis. Your p-value is very small. You can see here it's small p-value. If you lower alpha, that will also change beta, Eddie. So if you lower beta, that will also change alpha. So if you lower your beta, so lowering beta means you are less likely to make a type 2 error. So you are more likely to accept the alternative hypothesis, right? If you are more likely to accept the alternative, this will actually increase your type 1 error. So we'll increase alpha. Unfortunately, there is no optimal solution where you can decrease them both. If you decrease one, you will automatically increase the other a little bit. But there are ways to mitigate this by increasing the sample size. Cool, good question there, Eddie. I'm gonna take a break until 10 after, and then I'll continue with the next tutorial. No worries. Hey everyone, I'm gonna start again. It's so funny that I just did the tutorial from 9 to 10. I'm gonna do it again. That's cool. Hopefully everyone had a very good start to their morning. It turns out my morning has not even really actually began since I did not sleep last night. So I'm still basically to me, I'm operating as if it was last night. So yeah, but anyways. Oh, I was trying to finish something I had to do. So I could not sleep till I finished it, unfortunately. But it was a difficult enough task that it needed to be done over the entire, it needed to be done over the entire night. But it's okay, I finished it, so hooray. Yeah, it's really, the struggle is definitely real. Like, whenever people say that, like, if you did your work on time, it shouldn't actually end up behind. It's kind of like, sometimes it's not necessarily true, right? You have all these things come in at once, and you actually, even if you work very hard, you still get behind sometimes. But yeah, I just want to say that we were going over assignments, and it was noted that some reports actually had the dreaded library, the dreaded tidyverse thing in their reports, as if they hadn't actually used they had not used the message equals true or the message equals false, warning equals false thing. So sometimes the presentation of your ideas can in some sense be impeded by having too much clutter on your page. If you forgot to remove the tidyverse thing, you know that you're going to be using it for every single assignment. So it would be important just to remove it. It would probably help you guys, right, to organize your ideas a bit. So definitely remove the tidyverse, right? Because sometimes it does look a bit cluttered. I didn't remove marks if people just kept the tidyverse, no, but it's just that sometimes it becomes hard to read things, and when I'm trying to look over the tidyverse loading, people don't. It's not something to take off marks for. Losing marks be based on the actual quality of the write-up, more so than the tidyversing. But sometimes when papers look organized, I notice they look organized in all kinds of ways, right? So just trying to make it as organized as possible. Yeah, but no, we did not remove marks because people loaded tidyverse. Okay, so, but I did hear that in this assignment, you guys are working a lot with tidyverse, like manipulating data frames and stuff. So that means you're going to be using tidyverse quite a bit here. So it might be important to remove the loading of the tidyverse in your reports, because you already know it's going to come up since you're using tidyverse so much this assignment. I'm going to go over 3 important functions, which is the mutate function, filter, and select. I asked students in the last tutorial what they thought mutate was, because I think at this point, Ken has kind of elucidated it. And they gave me 2 correct answers, because there's really 2 answers here. The first one is that they said mutate creates variables, which is true. It does create new variables in your data frame, right, based on existing variables. And the second thing is you can modify variables that already exist. So if you want to create new variables, you can do it if you want based on the existing variables. And if you want to modify a variable, you can do that as well. Mutating means you're shifting your data in some way. Yeah, the data is being manipulated in some way, right? So, but usually mutate means you're adding another feature, or like basically you add another column to your data frame, right? Because even filter and select will change your data frame, but not in the same way as mutate. So mutate will always increase your data frame by the number of variables you added. Whereas if you do select, for instance, you can actually reduce the number of variables in your data frame. So while it does change it, not in the same way as select or filter, right? Because select will actually subset your data frame along the column space. It will reduce the number of columns, but mutate will always increase it, right? So yeah, it does create new, you can create new variables based on the ones that exist if you use your existing variables to create new ones. And you can also modify the ones you have. If, for instance, your variable is presented as a string, but you want it to be numerical, you could obviously create a new variable that says as are numerics of the old one. So you can update your variables and you can create new ones. So I'm going to use empty cars because I feel like I've been using it the entire semester. So it's my data frame. If you look at the data frame for empty cars, you're going to see that it has all these variables here. I'm going to, so I was telling them in linear regression sometimes when linear regression is equal to, you know, y is equal to mx plus b. We always, we sometimes want to recenter our variables, right? And by recentering, I mean that sometimes you want to recenter this one, right? So you want to, sometimes you see something that's like this, that's common, right? So yes, like this, you recenter it. Just because sometimes it's easier to interpret the change you see in y based on the change from the average. So you can say the value of x changes from the average by a factor of whatever the difference happens to be. Sometimes that makes more sense from an interpretability perspective, especially if you don't have 0 in your data set. So if your average is not 0, or so if the average is not 0, sometimes it makes sense to talk about the shift from the shift from the mean. Sometimes we transform these variables. So suppose we wanted to transform this variable and we wanted to add it to our data frame, we could. How can we do that? We can create a new variable called weight, right? And this is going to shift things. So if I do something like weight, you can see that, first of all, the pipeline goes from the left to the right. So I'm starting from the distance. I'm going to create data 2 based on data. And then the pipeline is I'm going to mutate by a factor of weight minus mean. So I'm going to create a new variable called weight, which is equal to weight minus the mean, right, of weight. So that's me recentering my variable, right? But you can actually see that, so this is recentering, right? But you can actually see that the initial data frame had a dimension of 32 by 11. This one, it doesn't remove variables, right? So it's going to have an extra dimension. And if we look at the data, we're going to see that it has this variable here, which will actually be negative when the weight, right? It will be negative when the weight of your car is actually less than the mean, and positive when the weight of the car is bigger than the mean, right? So I want to elucidate why it's actually so much more efficient in tidyverse. Notice that in one line, I actually manipulated my data frame in a very nice way. On the other hand, if you were to use base R, you first need to create the weight variable, and then you create a data frame that appends weight to data. So you are externally creating this variable and then adding it to your data frame. Now it does work, but it's just, if you keep adding too many variables, it will become messy and sloppy, right? Each time you'd have to keep creating new variables externally and adding it to a data frame. That quickly becomes difficult when your data sets are very large. So this is why we tend to use tidyverse, just more, it's literally tidy, and its name is the root word tidy. And that's not a trivial thing, right? It really actually is tidy. Yeah. So this is why we kind of use tidyverse to base R in this way, right? Cool. Now, I want to show you guys filtering. Because in your assignments, it's more likely you will use filter than select. Why? Because filter, guys, actually subsets your data along the rows, whereas select actually filters along the columns. So if we ask you to filter based on a particular characteristic, of your data or a particular observational characteristic, this is you using filter. But if he tells you he wants you to select certain variables, this is the select function, right? So select filters across the column space, whereas filter does along the row space. So they're not implicitly the same function. If you mix them up, you will not get what you want as a result. It will do something different. So make sure you're being clear about this. I made a little note here that says subsetting data across the rows. And I gave a little example, right? So the example I gave last class was I said that let's look at the cylinder variable within empty cars. You can actually see that it's a variable that has 3 different classes, right? So it goes 4, 6, 8. And so you might wonder if you want to do linear, if you want to do a model where you're looking at how weight is related to, like how many miles per gallon you go, you might think that the number of cylinders you have is in some sense related to how many miles per gallon you can go. Right, so I made a little plot here, right, to motivate why I might subset or filter based on a certain characteristic. So here I'm going to actually filter based on 8, but the question is, why am I going to do that? So I'm using data 2, which has the new variable weight we created. And you can see that from this thing here, and maybe I'll just blow it up here so you can so I can pull it up a bit more, which I didn't do in the last class, but we kind of need to see. You can see here that when I color it according to the cylinder type, it actually shows that the cylinder types have different miles per gallon. They're occupying different parts of the graph, right? So when you think about whether or not, if you wanted to become kind of linear regression model, you might think there's something inherently different about the 3 different groups, which might make you think that you need to have separate models. So maybe you think that, for instance, 4 and 6 are similar because there's some overlap here, but the 8 is different from the other 2 enough that you probably should remove it from the data set. That's possible if you want to do a model and you want to get something that's accurate. You might think to yourself, well, let me remove it because, for instance, these 3 points here are pretty far from the other points over here, and they all belong to cylinder class 8, right? So if you wanted to select in that way, you would have to use filter. Now, I was telling you that actually the filter function is kind of neat because it works like a Boolean series. If any of you took discrete math, what I mean by Boolean series is that when you give it a logical operator, it will evaluate the truth of that statement. So in this example here, I say choose a cylinder equal to 4 or cylinder equal to 6. So it will evaluate across the cylinder to see if they're equal to 4 or 6. And it will put true or false because it's a series. When it's false, it will drop those observations from the data set, right? So this is a Boolean series. It will drop the false because it doesn't satisfy the condition of being 4 or 6. Now, the thing I want to point out is that R is certainly less rigid than Python, but it still has its rigidity sometimes in the sense that you can't do this. It will not run. Right? You cannot do this. You cannot say, oh, 4 or 6. You have to specify that you're saying cylinder equal to 4 or repeat it again, cylinder equal to 6 for it to run, right? You cannot just aggregate 4 and 6 and say, maybe it's enough, right? So it's not that flexible. It will not load. It won't even know what you're doing if you do it that way. So you need to specify that you are looking, that you have to put cylinder twice basically, and cylinder equal to 4 or cylinder equal to 6, right? So it's going to gather only those cylinder classes that satisfy the condition, and it will drop the other ones, right? So you can see here that if I run this and I look at the dimension of my data, it's going, oh shoot, that's wrong. Dimension of data 4, I'm going to get 18 and 12. That's because I think there's probably actually 14 observations that belong to CYL 8. So I dropped it. I went from 32 to 18 because there are 14 of them, right? So Now let's suppose I want to select across the columns, this is a typo, columns rather than the observation. So now I can remove variables I'm not interested in. But what I cannot do using the select function is remove rows, right? Because filters, when you give a Boolean series and you evaluate the truth of a statement, that's you removing rows, right? What they don't satisfy the truth of the statement. But that's not true for the select function. The select function is actually pulling out variables that you want. It will drop the ones you're not interested in, right? So let's suppose I wanted to choose, for instance, so I'm going to go back to the initial data frame we created with the new weight variable instead of pulling out. So I'm not going to use data 4 that only has 4 or 6. I'm going to use the full one. So now let's suppose I wanted to do a model where I'm looking at, weight against MPG against weight. Then one thing I could do is I can select MPG and weight. So you can just recall what our data frame looks like for data 2. I created a new category called weight. So now if I run this, I'm selecting just those 2 variables. So if you look at the dimension of your thing, it will actually be, it will be 32 by 2, I believe, because I didn't ask for the other 2 variables. So if I look at the dimension of that thing, I get 32 by 2. Now, let's suppose I wanted to make a plot. Let's run this and see what we get. Well, I'm going to feed the data frame I created, obviously, that only has 2 variables. You can imagine that obviously weight is a function, is more stable than MPG. Like obviously miles per gallon is variable. So weight is more stable. So it's the X variable. Here's my plot. You can actually see, guys, that you get a line of best fits, and the extent to which your model does very good is obviously how close it follows the line. Does anyone know what those gray things happens to be? Ken did actually discuss those gray bars, not in this context, but he discussed them in general. Does anyone want to take a stab at what those gray lines happens to be? Yeah, those are standard errors, right? So those are standard errors, which we know is actually S divided by root n. Now, the extent to which your model did very good is the extent to which your standard errors are small around your estimates. So you can see that it did more poorly over here because you have more loose points at the tails, where it did it better over here. That's why the standard error is a bit tight here, especially here in the middle where it was almost a bullseye. But when you can see when your line does pretty poorly at estimating your standard errors, then of course your bands will be bigger, right? I use geom smooth to get this. If I did not put geom smooth, I wouldn't get that blue line with the points. You would just get like the following. Just to be clear here, you would not get that. You would get the following instead, which is just a series of points that does not really give you much of anything. You would just get this basically, right? But which is actually even worse than the plot we had up here, because at least this one tells you that there's some color effect. Basically, there's some effect in the the cylinder class. But anyways, you can see there that you can play around with the features of the actual plot. In fact, if you wanted to remove your standard, you can see first of all that it's doing a linear regression. It's saying y squiggly x. Y squiggly x is actually it's doing the following model. It's assuming the following model is true. The error terms are like normal. Right, so it's assuming this model here. So you can see y is a function of x. That's why it's doing y squiggly x. If you want to remove this, the default is to include the standard errors, but if you were so inclined, you didn't like it, you could of course put standard error equals false, but it's a bit contrived, right? Because it looks silly, right? No one publishes papers where they don't put their standard errors, because your estimate's only as good as how wide your standard errors happens to be. So we generally tend to include them. So it's a bit silly to just include them, but if anyone was kind of curious what it looked like without the standard errors, there it is. It's just a line of best fit but you wouldn't necessarily know much about, yeah, like performance, right? Because you wouldn't have the standard errors around your estimate. So that's something to consider, right? That's enough of that. What I want to show you also on your assignment, so Ken's going to introduce power, and I want to give you guys a bit of a heads up there. And last time I introduced alpha, and I think I said alpha is equal to probability of a type 1 error, right? Anyone know what this is? What is a type 1 error? Anyone know what the type 1 error happens to be? So it's a probability of rejecting HO given HO is true. So it's the mistake you made. Yeah, it's a false positive. Exactly, it's a false positive. Right? I.e. is a false positive. Which is not good, right? Not because think about it. In the court of law, it means that you let somebody that was innocent. Oh, this is awful. It means you let somebody that was innocent go to prison. But even in medical treatment, it's pretty bad because you told someone that was healthy, they were diseased, right? So neither of them is very good. On the other hand, so obviously we always want to minimize that type 1 error. Beta is type 2 error, which is, the probability of rejecting HA given HA is true, right? That is, you have a false negative, right? So this is to mirror what John is saying. This is actually a false negative, which is equally pervasive, right? So in the court of law, false negative would mean that somebody was actually guilty, but you didn't convict them. In the medical trial, it's even more severe to the type 1 error because it means somebody's very sick, but you told them they were healthy, which is in some sense worse than telling someone they're sick when they're healthy because they wouldn't have the opportunity to seek treatment when it was in the earlier stages. So that's probably very problematic, right? So we try not to make either of those mistakes. In the last class, someone told me, is it true that somebody asked, is it true that if you, somebody says, is it true that if you decrease alpha, that you increase beta? So this is the question, right? So the question a student asked was the following. If you decrease alpha, does that imply that you increase beta? Right, and I said that, yes. And they said, why? I said that, unfortunately, the probability of making a type 1 error, this is in the null space. We're talking about whether or not you reject HO when it's true. Beta is in the alternative space, right? They're not, the solutions to both these problems are not even in the same space, right? In convex optimization, you guys know from calculus that a global or local maximum exists for a set of observations because there's one unique solution, basically, right? If you can determine that there's a unique solution when you maximize and things are convex, right? But here, unfortunately, and they all exist in the same convex space, basically. The problem here is that this doesn't exist in any kind of convex space. There exist in separate solution spaces. So a solution for one problem is not for the other. And unfortunately, you cannot simultaneously decrease them at the same time. Why is that? Because if you are less likely to reject the null hypothesis, this means you actually decreased alpha. This means that you're actually also less likely to accept the alternative. So if you are less likely to accept the alternative, you will by definition increase your type 2 error. Unfortunately, you cannot simultaneously decrease them. And similarly, if you decrease beta, so you decrease your type 2 error, you are then more likely to accept the alternative, and you are less likely to accept the null. So you will increase type 1 error. You cannot simultaneously make them equally small. You can do things by way of the sample size and the effect size to actually decrease them both, but not at the same optimal way. One has to remain bigger if the other one is small, and that's just what it is, right? So it turns out that power is actually 1 minus beta. So 1 minus beta is equal to power. So we actually aim for 0.8. You can see that the only way power is 0.8 is if beta is 0.2 when alpha is 0.05. So you can see that your beta is higher than alpha. They cannot be equally small. We aim for a power of 0.8, and that would be considered good for an alpha level of 0.05. Again, you cannot make them equally small. An alpha of 0.05 can never yield a beta of 0.052 for the reason I stated. They're not even in the same solution space. There is no optimal solution that satisfies them both, but we can try to make them as small as we can so that when alpha is 0.05, beta is getting close to 0.2, right? So this is something we have to accept. We cannot make them equally small, unfortunately, because of the way the solution space is set up, basically, right? Is this clear to people? Why we have this problem, we cannot make them equally small? Let me know in the chat if it's not clear, because this is something that's going to be pretty important as it pertains to what do you call it? Making sense of power, because you're going to ask this in your assignment. So it's important that it's clear to you guys. If it's not clear, let me know. Otherwise, I'm going to assume that it's good. I'm going to move on to things that you can do to mitigate keeping those two things small. So I'm going to assume you guys understand. Okay, so there are a couple of things we can do. And really, the two things we can kind of do to make them both small is to increase the sample size and to increase the effect size. So increasing the effect size, guys, it means that the difference between the null hypothesis and the alternative should be very big, right? So by that I mean that your data, your evidence in your data should be that much different from your null hypothesis to result in a situation where your effect size is very big. The difference is big, right? And what do I mean by that? Remember, your t-test is actually equal to, so t is equal to y bar minus mu over s divided by root n. So this is for the null hypothesis, you know, mu is equal to mu naught. See that the effect size is this thing here. This is the effect size, guys. So this here is the effect size, this thing in red. Obviously, the bigger this thing happens to be, the bigger your t-test is going to be. The t-statistic will be big when that difference is pretty big, right? So the t-statistic will be big when that difference is big, and that's what I mean by a large effect size. When the difference between your y bar and mu is big, of course, your t-test will be very big. If the difference is small, of course, your t-test will shrink, and that's when, like, if you want to see a very big effect, right, then of course you want the difference in your observed statistic and what you hypothesize to be very big, right? So for instance, with COVID studies, if people want to show the vaccine's effective, you always assume, so in the null hypothesis is always you assume that there's no effect, but you want there to be an effect. So what you really want is that the difference between your null hypothesis is where there's no effect, and the alternative is you want it to be very, very big. So you can say, hey, you know, there is an effect, the treatment actually worked, right? So that's what you're looking for. And so that's one way to mitigate making the beta and making the beta and alpha small, the errors. The other thing is the sample size. Again, this is related to the t statistic, right? Because you can see that this is a standard error, which, you know, Ken was pointing out to you guys. So this is a standard error that when the standard error is very small, your t statistic is very big, right? So of course, the standard error is the variability you have within your sample, right? If the variability within your sample is big, guys, then of course what that insinuates, right, is that if the variability is very big, what that would insinuate is that your t-test will actually shrink, right? Because if you have a big variability, then this whole thing is very large and will actually make your t-test go down, right? Because you're dividing your effect size, which is y bar minus mu, by a very big standard error that will actually make your t-test shrink, right? So if you can imagine the distribution along the null here, right, and your t is equal to 0 is here, and your reduction regions are over here. If your standard error is very big, you will actually shrink your t statistic as far as you can to 0. So it will go closer to these regions here where it's not where you filter reject the null hypothesis, right? So when you increase your sample size, the standard error will actually get smaller and it will blow up your t statistic, and you will be more likely to be in the black regions, right? So those two things together will mitigate making your p-value and your beta small. Of course, the last thing is the significance level, right? Because like I said, if your significance level is actually increasing, then of course your power, if your significance level is actually decreasing, your power will have your beta will increase, right? So the last thing is to mitigate the power is that obviously, if alpha decreases, that implies that your beta will increase, unfortunately, because like I said, they're not in the same solution space. If you decrease the odds of rejecting the null hypothesis, it means you're more likely to always reject the alternative, and that will increase your type 2 error, basically, right? And then if this is increased, that has to insinuate that your power, which is equal to 1 minus beta, of course, is going to go down, basically, right? So you will decrease your power. So it's also related to alpha, right? If your alpha is decreasing, your power will also decrease, right? So those are 3 things that really influence your power relationship. But while we can't always help the third, the third thing we can always kind of make sense of the first 2 things, right? This is an example here. This is what I did last week here. This is actually why I didn't tell you guys completely back then why I chose the mu to be 2. It's because I know the difference between, like the actual mean in the sample, remember, was actually 3.21, I think 5, and then mu is, I hypothesized to be 2.0. Now this effect size is actually pretty big, right? So for an n of 32, a difference of 1.2 is actually pretty large. So I knew that I would fish for a p-value, which you shouldn't fish in general, but I would fish for a p-value that's actually going to be significant because the effect size is large, basically, right? So if I run this, you'll actually see that you get the p-value is very, very small, right? It is, in fact, 6.67780, which is p-value certainly less than 0.05. So you can see p is less than 0.05. So we will reject HO. So this means that if you ever were to make an error, you would make a type 1 error because you reject a null hypothesis. Now, if I actually shrink the effect size to 3, you will see that it will actually result in a p-value that's too big. Right, so now you can see that the p-value is actually bigger because now what it's saying is that this difference is actually only like 0.2115, right? It's 3.21 minus 3.0, which is 0.21. That effect size is too small. So the t statistic is actually shrinking closer to the null hypothesis, which is right here. And as a consequence, your p-value is actually kind of big because you can see the area above where it's close to 0 is kind of big, right? You're probably making a type 1 error is too high, so you will not reject the null hypothesis. Now, as a conclusion is that if you don't reject the null hypothesis, your power goes down. So you can see here your power is going to decrease because you are less likely to reject the null hypothesis. So you can see the effect size, one way you can actually manipulate things to, get the effect you want, which is actually kind of problematic because there's something called p-hacking where people fish for a different result because they know that the effect size being large, for example, can result in a small p-value. And they also know the sample size being large can result in a small p-value for the reason I said that it shrinks this thing here, which will make the t statistic bigger. So this p-hacking is pretty significant. It's pretty problematic sometimes, which is why we have to do simulation studies often. The simulation studies where you repeat the study many times, you're less likely to get some dastardly things when you p-hack. People can catch your p-hacking more when you reproduce the effect more than once. If you just look at the effect once, it's hard to catch p-hacking sometimes, especially if you only saw one glimpse of the data. If you keep seeing different independent data sets and you look at some kind of distributional thing, p-hacking becomes a little less likely, basically. Yeah. So now let's see what happens. Let's put a context on this. It's a little more interesting. So I'm going to sample from a distribution I know is actually mean 3. So you can see here that, oops, you can see here that first I'm going to do 10. I'm sampling something that's normal. Now I set the seed, guys. Basically, I've set a seed of 1. You can set the seed to whatever you want, but it will just change the index from where it starts. So it will pull from a different part of the normal distribution. If you don't set the seed, actually what you'll see is your results will change, right? So you see that if I do this once, then if I do it again, I will get a different set of things, right? So if you keep doing it, you'll get different things. So because it's a random generator base, it will randomly choose different things. So you should get different numbers. It will take different permutations. So make sure if you want to see the same, want to see something consistent, you set the seed. But anyways, I know for a fact that the true mean is 3 because I said it that way, right? Now, if I do a t-test based on this, and by the way, you might say, why are you doing a t-test when your sample size is so low? Are you able to even assume normality? In this example here, I can, because I know I sampled from something that's normal. So I already know my random variable is distributive normal because I sampled from a normal distribution. That's why I'm able to, I'm able to do a t-test, even though my sample size is very low, because I know for sure the distribution is normal. I chose in that way, right? So yeah, just because you might think, well, how come, right? That doesn't make any sense. But yeah. So let's run the t-test. You guys will see that you get 10 observations. Now the data will show p-value of 0.0013. You might say, what happens if you increase the sample size, right? Because I did say one way to, because first of all, I know this is a significant result merely because I know for sure it's the mean is 3. If I increase the sample size, it will become more significant. So I'm just going to block out the value of X running because it's 100 data points. If I turn it to 100, you'll see that the p-value is even more significant. That's because the t, what happened here? Notice that initially the t-test was 4.586, right? This means that it's somewhere like maybe over here. Let's suppose this is like 4.5. Right, but when you drive your standard error to when you increase your sample size, it actually makes this standard error go down even more because it's divided by root n. So your actual test statistic is now further into tails. Maybe it's somewhere over here where it's 12.6 or whatever. It goes even further into tails. The p-value is smaller. This is what you get when you decrease the sample size, right? It makes your effect size more significant. Now, obviously, if I change the mu to 3, then of course you're going to get a p-value that's not significant because, right, you can see that your true mean is 3 and you hypothesize that it's 3. Of course, it's going to be a p-value that's largely insignificant, right? So that's how the effect size also works with sample size. When your effect size is small, you will yield a very high p-value, right? Okay, now I'm going to make a cool function. Well, it's actually Ken's function, but it does cool things. Right now, in this assignment, you may simulate things. Tidyverse is kind of cool because it allows you to simulate things multiple times. Rerun is a function in tidyverse that allows you to rerun any test you're doing n number of times. Here, I want to rerun my test 1,000 times, right? 1,000 times, I'm going to sample from a distribution that is normal, and let's change the mean to 10. So I can do it first and I'll show you what happens. So change the mean to 10. Change the mean sample size to 10, but the mean is still 3. Now, when it says map, it's mapping those observations. You can see that every time it runs a test, it's going to pull out a different sample size 10, and it's going to send it right to this T function here. So it's going to perform 1,000 different T tests. It's going to literally pull each observation X and shove it in here. Then it's going to spit out a p-value. It's going to map to a p-value data frame, and then I introduce a count basically, right? So end frame is me calling I labeled my values p-vals, and then I'm asking it to count the number of times my p-value is less than 0.05. Right, so let's do that. Let's see what we get. P-value less than 0.05. Well, let's run it and see what we get. So I did say that I want, in theory, that p-value to be less than 0.05, and I want my power to be less than 0.2. Right? Now let's see what we get. First of all, I'm gonna count out. So 191 divided by the sum of 191 plus 80. This is the number of tests. So you can see that 0.1929 is the output. What is this? Do you guys know what this is? What is 0.1929? What is this? What have I just computed here, guys? Does anyone know what I've computed here? What is this? Any guesses? Come on, someone's got to have a guess. No guess? So this is actually beta, right? This is actually beta, guys. And this is important. This might be important for your assignment. This is actually beta. I've computed beta here. So power is 1 minus the beta. So it's actually 1 minus 191 divided by 1. You know, I made a mistake here. Yeah. So this is actually, your power is actually this 0.8. This is actually power. So 181. Yeah, that was a mistake. It should be 191, Callie. I realized, right? I was like, it's 191, not 181. It's 191. Yeah, that was my goof. Totally a goof. So those numbers come from, so what it's doing, John, it's actually evaluating the number of times your test shows significance. So it's evaluating the number of times your p-value was less than 0.05. Remember, even if there is a significant result, guys, there's always a chance. So even if there is a true treatment effect, there's always a chance your test messed up, right? So you got a sample that was bad, that yielded an insignificant result, even though it was actually true, right? So that means that there's a chance that your actual test yielded a p-value that was bigger than 0.05, because there's always an error, even though we know for a fact the true mean is 3. So that's a true error, basically. We know the mean is 3. So it's actually, sometimes it's actually failing to reject the null hypothesis, and it's saying the true mean is 2. It's doing it 191 times, which is a false conclusion. That's the type 2 error we've computed here. So the power being the complement of this is 0.8, which is what we want to see. Now let's see what happens, guys, if we drop our alpha. I did say, if you reduce alpha, you will increase beta. How exactly? Let's see what happens. Now beta is actually 488 divided by 1,000. Your actual beta has now increased to almost 50%. Right? So now if you want to compute your power is really down now because your beta is up, basically. Right? So if you decrease your alpha, it means you are less likely to reject the null hypothesis, even when it's false, because you have now decreased the chance of doing it if you're rejecting the null hypothesis, because now you're asking for rejection. If you're really further, you're now asking for rejection if you're far out here or over here, which means you will actually not reject the null hypothesis if it's in this black region. So you're even more conservative, and you're going to dismiss the null hypothesis being false if it's over here or here. You're now asking for even further evidence in the tails, right? So now you're gonna make the error more often. sometimes this can be mitigated by increasing your sample size, right? I did say that if you increase your sample size, sometimes you can fix it a bit. What happens if you increase your sample size to 100? You can see here that your true is 100, right? So 100% of the time, it will correctly make the conclusion that the null hypothesis is false if you increase your sample size. That's true in this context here, because the true mean truly actually is not 2. You should not expect that if you increase your sample size to 100, it will make your beta 0. It's only true in this case because we know the mean is 3. But in real data, it doesn't look that nice. You will decrease your beta by increasing your sample size, but not to this extent, basically, right? So you can actually play with the function quite a bit to see how they kind of change. So for instance, if I change my mu to, let's say, I don't know, 2.5 or something, even this, changing the effect size will change the significance a lot, right? So let's see what happens if we change the effect size. Notice now that when your mu is close to 3, because it's only 0.5 difference, your type 2 error goes up to 0.69%, right? So your power is going to be something like 0.3 or something, which is pretty bad, right? So you can see that if your effect size is pretty small and your sample size is small too, that will actually make your standard error kind of big. The within variability is too big and you cannot reduce it because your effect size is small, but this is kind of big. It will make your t-test really small, closer to this region here, right? If you increase your sample size a bit, or even let's say to 50, just see what happens. It will probably reduce this problem a little bit. You see that it reduces the false rate. Now that you see that if you even increase sample size to 50, it will actually reduce your beta. So you can see the sample size matters quite a lot, guys. That's why we always keep saying asymptotically, because the sample size is very large. We are very, very interested in sample size sometimes because large samples, does have a way of, making our effect look nicer. But that's also problematic, right? So we shouldn't p-hack because we know sample sizes increase things. Scientists can always find significant results if they drive their sample size like 1 million or something. So we're always very astute to make sure we're not cheating in that way. We're taking huge sample sizes to cut into your effect. That's not cheating, basically, right? So we try not to do that as well. But yeah, it's kind of neat. I think that statistics is kind of cool. You can see how, yeah, you can play along. I would encourage you guys to play along with this function a lot because not all the ideas might be clear, but if you kind of play with it a lot, like just take the rerun thing here, manipulate the alpha level, the sample size and the effect size and see what happens to your beta. But it's not a surprise to me that this wasn't exactly obvious that you're computing, it's certainly not obvious that you're computing beta right away, but when it becomes kind of obvious when you realize that when you look at the effect size, so when you look at the error, you should get something like, sorry, what did I do here? Why is it doing that? Oh, I know, it's because of this. Let me go back. So yeah, for an alpha 0.05, we always look for a beta of, I guess, 0.5. So you can see here that, yeah, it does something like this, right? So it goes to 0.2. I actually left a couple of other codes here for you guys to play around with. You can actually see, and I left some comments here because I don't have time to teach them, but you will see that I left you some kind of things like some things you can run to see what happens. You can graphically see the relationship, for instance, between power and sample size, where if you keep increasing the sample size, your power gets closer and closer to 100%, which is obviously unrealistic. We usually get around 0.8. But you can see that if you increase your sample size for a particular delta, your power will obviously increase, right? And you can change the delta if you want. So delta here is actually the effect size. You can change the effect size if you want. To see how it changes if you increase the effect size. If you increase the effect size, it will change the powers for sure, obviously. And if you increase the sample size, it will also change the powers, right? So you can play around with the functions I left you here to see what happens. I also left you a function to see how the power function works if you change the alpha. And I did the same with the effect size as well, leaving comments. I realized I didn't have time to do it all. but I did want to show you guys some stuff. So if you want to keep reading the tutorial I gave you guys and playing with the code, you will see how those three things are working together. It's kind of neat. And sometimes it's, I think simulations give you some statistical intuition. So pair out those things, see how you feel about it. If you don't, if you're still feeling unsure, put it in the chat or discussion. Ken will probably see it. But other than that, have a great morning. That's it for today. I'm gonna stop the recording now and leave you guys to enjoy your morning.